All right, so chapter 2, we're going to do 2 in one day. All right, so on every schematic you have lines. All right, lines are used to connect from power sources, control devices, loads, and an electricity return or hydraulics return to power source. Excuse me. So lines are meant to connect. So that is what you're trying to trace whenever you are working with schematics. Now, what you have to really pay attention to, if you ever are drawing a schematic, you need to make sure you draw your lines correctly. Why? Because of many reasons. Okay? We'll go into those. Circuit layouts. The placement of the equipment is never as orderly and neat as a schematic. How many times does that happen? Answer, never. I don't even think when somebody's wiring a house that the lines are all nice and neat. I'll give you for an instance. Whenever I draw any kind of schematic, so let's say, I draw a schematic for a hydraulic, so here's my reservoir and all that. My whole schematic might be right here. Does that mean my reservoir is right next to it? No, it's probably 3 rooms away and hidden in a closet. Okay? Same for your power source. Whenever you're drawing up schematics for a house, is the panel right next to where your plugs are or where your light switches are? No, it's generally either in the garage or tucked behind some place where nobody can get to it, right? So it's never really that neat and orderly. It's kind of something you end up having to deal with as things go on. It can be changed due to the fact that some equipment needs special support. If it carries a lot of weight, do I want to put it on the 2nd floor? Probably not. Probably want to put it on a reinforced concrete floor. I'll give you for an example, the big robots in there. They have to have a certain depth of concrete for the concrete anchors to be used, or else the robot can tip over from its own weight whenever it starts slinging itself around. Think about that for a minute. How much equipment do we have like that? A lot of basic equipment, right? Take your hot water heater in your house, for example. There's a couple of different examples I can use with a hot water heater. One being, if you ever sever all safety mechanisms. Anybody seen Mythbusters? What happens if you destroy all the safety mechanisms? It's going up into the sky and it's going to take your house with it. That's basic maintenance. Make sure all your safety valves work on your hot water heater. But you also have the fact that it's containing a lot of water. So I might want to make sure I've got a drain nearby it to make sure any water that comes out is not sitting in a giant puddle in my basement, right? So special support. There are many times where you install a piece of equipment and you've got to reinforce the concrete, you've got to reinforce something. Why? Because reinforcement is going to allow it to stay where it's supposed to be, not on the ground or through the ceiling. That has been known to happen too. Okay. Special ventilation. Why do we need special ventilation? Because some machines overheat. What does it cause? It causes total meltdown. So if you don't have enough ventilation for some machines, they overheat and they shut down. That's why a lot of machinery is involved in very big open air spaces. Why? Because we can cool an open air space and the machines are not going to overheat nearly as easily. If you put something in an enclosed space, how easy is it to heat an enclosed space, a small enclosed space versus a large open space? Okay. Special structures. So if you have an overhead crane, you can't really have an overhead crane unless you have rails overhead, right? That's just one specialized structure. There's lots of others. And needed power supplies. If you don't have power run to something, you might have trouble operating the electrical thing that you're trying to operate. Make sense? Circuit layouts are never as easy as what they are assumed to be. Okay. Circuit layouts are very rarely what they are and where they need to be. Okay. So needed power supplies might have to be run to it. You might have to beef up the floor enough to hold it. That goes back to being able to read concrete schematics and know the thickness the concrete needs to be and the interior structure that concrete needs to be. Right? If I've got to hold up a 2-ton robot without my floor cracking, then I might need to reinforce that concrete some more. It happens. All right, all systems. So there's 3 main types of systems. We have piping, fluid power, and electrical. These are not all the systems in the world, but those are the 3 biggest ones that we run. All of them work, I won't say completely the same, but mostly the same. You have 3 things that make up a basic system. Go ahead and list them. You have 3 things that make up every basic system, no matter what it is. And this is why it says that they work the same. Because they do and they don't. Some need more specialized things than others. But you will always have a source of your power. Okay, in electricity, that's a battery, that's the electrical lines. That is something that is putting power in your system. In hydraulics and pneumatics, you have a compressor or you have a pump that is pushing fluid, either air or actual liquid, into your system. In piping, you just have to have some place for stuff to go into the pipes, right? You have to have a path. You have to have a way for whatever you're trying to push to get where it needs to go, right? And then you have to have a load. You have to have a place where something is doing something with what you just sent into it. Does that make sense? So think about it like traffic. The source is you coming from your house, path, streets, yes, and then load. You're going somewhere to do something, right? Why do you leave your house? You're going somewhere to do something. Does that make sense? You left your house for some reason. That's your source. You're driving down the streets. That's your path. And let's say you're going to the grocery store. You're going to go wander around the grocery store, find dinner for tonight. That's your load. Okay? Basics of every system. So wire allows flow of electric electric current. Fluid conducts in pipes. Okay. So a breakdown in any system is the result of an interruption of flow. And that is true. So think about what would be a breakdown in your drive. What is the one thing all of us hate to encounter when we drive? Traffic, right? It stinks to sit in traffic. But there you go. So that would be a breakdown in the system. Traffic should flow, but let's say somebody decided to play a little bit of bumper cars. There's your breakdown, right? So all systems follow three basic things. You can find your source, you can trace your path, and you will find your load. So arrows show flow on piping circuits. Flow is negative to positive in electrical. What do we typically think electricity flows from? Is it negative to positive or positive to negative? Our brains tend to tell us, no, it's got to flow from positive to negative, right? Reality is it flows from negative to positive. What is moving in electricity? Anybody remember? Huh? We're moving electrons. What is the charge of an electron? It's negative. So it's looking for something positive to go jump to. That's why it flows from negative to positive. That's why it flows from negative to positive. You're moving electrons, you're not moving protons. Which is actually, I'm not getting into that. Short dashed lines. Okay, so this would be figure 2.1 in your book. Like I said, I hope y'all get your book soon. So you have drain or return lines, you have exposed wires, you have vents. It always depends on what you're looking at. So solid lines have different meanings because solid lines could mean if it's electrical, wall concealed in it's a wall concealed wire, which we like to do a lot because we don't want to see wires hanging around our house, right? Because it kind of would just look messy. If you truly saw the spaghetti that is in your house, it's not a very neat thing to look at. It just looks messy. You have fluid power, which means if it's a solid line, it is a working line. You have piping, which this could be considered as a pressure line. You have large dashes. There's all sorts of different types of lines. If they're done in large dashes, that could mean that it's a floor concealed wire. If it's fluid power, it could be the pilot line. If it's piping, well, there's not really apparently one for piping. So this is figure 2.1. So electrical, you have several different types. You have the wiring concealed in the wall, concealed in the floor, exposed, 3 wires, 4 wires, turned up, turned down. What it means by turned up is wires that, most of the time we try and run wire on the same plane. Why? Because it's just easier to do it. I can cut into it at any point and add more plugs. But there are times where I might need to turn it 90 degrees up or 90 degrees. Oh, there's my pen. I need to either turn it up or I need to turn it down. Why? Because I might need to take it down to the next floor or take it up to a light switch. That's all that's about, guys. That's why it's turned up or turned down. Fluid power, you have your working line, drain line, which when would you need a drain line? More often than you think. If it's hydraulics for the drain line, you might be trying to pull off excessive fluid in the system to keep it from overpressurizing. If you're doing it in pneumatics, you're trying to pull off any moisture Because what do we struggle really with in pneumatics here in the South? What is coming to bite us now because we're hitting the summer months? The humidity's starting to crank up, right? It's that point where you're going to start feeling like you need to have gills. Why? Because you are breathing literal water in the atmosphere. What do you think that does to hydraulics? What do you think that does to pneumatics? Because pneumatics is pulled straight from the air. Whenever you take all the air that's got all this water and you start compressing it, basically it'd be taking a damp towel and you start balling it up into your hand and compressing it in your hand. What's going to happen to all that water? It seeps out. Do we want that water in a pneumatic system? No. So what do? We drain it out to the best of our ability. I said that's the biggest thing with pneumatics is you've got to make sure you keep that drained out, because if you don't, it will make you regret it, if nothing more than with rust. Rust is never pleasant. All right, so you have ways to show direction of flow. Those of you that have been in my hydraulic pneumatic class, what does a colored in arrow mean? That is a hydraulic line. If it's clear like that, very good. It is pneumatic. And then you have the pilot line, which pilot line, all that really means is that you're using either the air or fluid already in system to change the state of a valve. We'll get into that more when we get towards that. Piping. You have non-intersecting lines. How do I know they're not intersecting? Well, because intersecting lines have a dot to them. Okay? And we'll discuss this more. But anytime you have lines that are actually physically connected, not laying over each other, but they are making a physical connection, like you come to a T or you come to a four-way path, it will have a dot to show connection. No dot, no connection. Okay? Clear up that confusion now. Because believe me, that happens a lot more often than you'd think. All right, so you also have your airline. So piping is used a lot. In this case, they're talking more towards the HVAC side, which is your heating, air conditioning, and such. So you have to have air lines, gas lines, you have a vacuum line, low pressure steam line, vents, cold water, hot water. And these are all stuff you need to distinguish, because if you are anything to do with HVAC, you're going to be messing with a lot of different types of piping lines. Why? Because it is a very complex system. That's why they get paid really good, really well to do what they do. Okay? Because they not only have to deal with electrical, they've got to deal with basically fluid power as well. That is both hydraulics and pneumatics when they're dealing with it. So pipe size with legends. Okay? So the biggest clue that this would not, excuse me, let me back up. If I am trying to set up this particular schematic, again, this is a language that you would have to learn, yes? We're going to learn a little bit of it, just enough that I can really at least recognize it. But this is for piping. Okay? And it's talking about different thicknesses of the pipe. Now, why? Why do we need different thicknesses of pipe? Well, because some need more pressure than others, and some handle more volume than others. Yeah, held together. All right, so this starts off saying that this is your legend. So any thick line is going to hold 600 psi, and it's the main line. My guess is this is dealing with a lot of hydraulics. Why? Because if you have 600 psi and you're dealing with any kind of a fluid, which it's talking about steam and soot, you're dealing probably with mostly, this actually looks like HVAC. All right, so this is HVAC. So you have a thick solid line down here. That's bringing in your main pressure. You have branches off that carry a lesser pressure that are going to other systems. So just like with electrical, we have a main line that's bringing in, let's say, 20,000 volts on most power lines, at least. Let's just say any voltage on a power line is more than enough to fry you. And yes, it can and does fry you. That's why you do not play with down power lines, right? Everybody remember that little spiel from elementary school? So same thing here. You've got a large line bringing in large pressure. And just like at your house, where you pull off only 120 volts for most of your house, what's the other voltage in your house? About 240. That applies to things like your washer and dryer, your stove, your hot water heater, things that are generally a very different plug and you do not plug into it for good reason. So you got some different lines that are pulling off a lesser pressure. Then you have your steam supply line going to your main line, but there is no connection point here in any sort of valve. So I'm guessing it has a small opening there, but I don't think they use the right symbol. But in the case of this particular steam supply line, you see that it has a little horseshoe over the main line. Why? Because it means that it is not what? It's not connected. So basically it's saying, instead of a connection, I've just got two pipes sitting on top of each other, one sitting on top of the other. Okay? You've got your boilers, you've got your soot line to blow out. Why? Because anytime you heat anything, you might have a little bit of soot build up, and you do not want to build up soot. It can clog a lot of things. So standards. Why do we have standards? Why do we standardize things? Keep confusion down. What did everything used to be? Let's say we're back in the 1800s and I need a set of nails because I'm trying to build a box. So I go down to the farrier or to the blacksmith and have nails made. Or is every nail going to be the same? No. Why? Because it is non-standardized work. It is not mechanical work. It is a human literally taking a piece of iron or steel, heating it up, and beating the crud out of it on an anvil until it gets to the correct shape. Yes? Nowadays, we have standards. Because nowadays, we have things like, if I say, here is this screw, I do not know the size, I can go down to the hardware store and what? I can size it. I don't have to go to a blacksmith and say, can you make me something similar to this screw? At which point they will probably laugh at you these days and go, why don't you just go down to the hardware store? All I have to do is just go up to my hardware store and say, screw, please match. That is why, and this is really true of everything, there's not a whole lot of specialized work going on with specialized anything. Why? Because if you want to work on something, you have to be able to work on it, right? Kind of like a car, an engine's an engine. You only have two different types of, let's say, screws or wrenches or anything like that, right? You have your metric and you have your standard. We don't have bolts that are somewhere in between. You're either dealing with metric or standard. So not only have we standardized physical objects, we've standardized symbols. Okay? Why would we do that? Why do we standardize symbols and schematics? Huh? Make them common? Well, the biggest thing is, let's say I've got a friend from Japan that's moving over and is going to come join me in maintenance work at Broza or any U.S. Steel, wherever you want to call it. If he's from Japan and he comes over here, he needs to be able to read the schematics, right? If I end up going to Japan and decide I want to go play maintenance worker at Japan, I need to be able to read the schematics. I might not be able to speak the Japanese language, but by heck, I can read the schematic because it is a universal language. Does it make sense? So what we've done by standardizing these schematics is started to create a universal language. So if I happen to sit there and go, well, I need a PLC from Germany, I can read the schematic on that PLC and use it just like I could one from here in America. Okay? That is why we standardized. So we can have small variations in drawings. I'm not saying you can't have small variations because let's say you have a specialized something or other that you only get from this one company and you have to have this as a special order thing. But if you have this special order thing, 9 times out of 10 you should be provided for a schematic with a legend saying, this is a specialized thing, here is what I used as the symbol for it. Right? If you want to talk about, let's talk back about maps. How do I know a city map from, let's say, a zoo map? Well, a city map's going to have different streets and roads. It's going to look like a city map. A zoo map is a zoo map. Generally, it has animals on it, right? Or it has the animal's type. This is the predator enclosure. This is the herbivore enclosure. Here's the monkeys. Ooh, ooh, ah, ah, right? So variations are provided for in the legend. All right? Here's the symbol for you are here. Generally, it's a what? It's either a little dot that's very visible or it's like a little star that's visible. So you can sit there and go, you are here. Oh, here is where this big giant red thing is a dot or star. And here's where I want to be. And I can just kind of follow my way. But it gives itself away. Okay? Yep. Yes, it's out the door, follow the hallway all the way this way. It's the only other hallway on this floor. Nope. All right. This is all stuff we're going to talk about anyway, so I'm not going to open these real quick. Okay. So symbols have become standardized. Why? Because anybody from anywhere needs to be able to communicate with somebody from somewhere. Right? let's put it this way. If you work for Broza, what nationality is that company from? It's German. You think they don't have German equipment? And that you don't need to know at least some of the symbols from that German equipment? Oh, but hey, the symbols are standardized. So even if the equipment is German, I can still work on it. Where's Mercedes from? Hmm? Now I'm doubting myself. I thought, now I'm really doubting my insanity because I'm trying to remember all of a sudden. I can't remember. Okay, so it is German. That's right. It was from, based on Carl Benz. I think I was thinking about Renault. That one's French. So basically, any equipment from anywhere needs to be understood by all people. That's why we standardize the symbols. So the standard symbol for a diode is this guy. And again, a diode is a one-way bridge. How do I know it's a one-way bridge? Because if I try and put something this way, I've got a wall blocking me. If I push it this way, that tells me that I'm pushing it through. Does that make sense? And then we have, what is this? For those of you in hydraulics pneumatics, that is a check valve. What does a check valve do? It's a one-way valve. Okay? It's supposed to stop flow going in the opposite direction. So if flow goes correctly, it pushes the ball back and flow can come from this direction. However, if my flow tries to reverse, it pushes the ball into the socket and no flow will come through. And then lastly, you have, this is another check valve. I can't remember the name of it right now. That's another type of check valve. This one that you can actually see. Again, it's all about flow staying in one direction, not reversing. Excuse me. All right, so these are refrigeration drawings. So you have electrical diagrams for a refrigeration system, and you have a piping diagram for a refrigeration system. Excuse me. How do I know which is which? If I didn't know which one was which, how would I know? Well, first of all, I can try checking my little boxes on these right here. Doesn't really give me much. It says it's a chilling chamber refrigeration system. That doesn't help. Okay, so I start looking for symbols. That symbol right there. That's a disconnect, aka a switch. If I see the switch, that's got to be what? It's got to be electrical. And generally a fuse is not drawn. The symbol for a fuse, after I drop my markers, symbol for a fuse is this little snaky thing. That's symbol for a fuse. That should also clue you in. The other thing that could clue you in, those of you that have had motor controls or have had PLCs, you have your contacts, their relay coils and things like that. Those are the things you look for to clue you in. This is electrical. If you're looking at the other thing, what you're looking for, your clues on that particular one to show you if it's piping, if it's electrical or anything, you start looking for valves. an expansion valve. Start looking for anything that will tell you what this is and what it's doing. These little valves right here, we'll talk a little bit more about those, but those are, I'm sorry, those are not valves, those are 90-degree bends. Those are meant to tell you, hey, this is pipe. Okay. All right, questions on that one? So identifying symbols. Many symbols look like the device they stand for. They generally do, right? There are some that are the exception to the rule, but 99% of the time, I'll say 90% of the time, there are more than a few exceptions. Most of them look like the device you're looking for. So if you're looking for a T in piping, it looks exactly like a T. Okay? If you're looking for a gauge, it looks exactly like what it looks like. You can combine symbols. So 2 or more symbols combined can make a single symbol. Piping symbols are one of the most often combined, as shown here. Because what we do with this is we take not only the symbols, so for the all right, so the symbol for a T is basically a T. You have a 90 elbow. Now, I don't think I could have done that any worse. Where's my rag go? Okay, I just had a rag. There it is. So you have a 90-degree elbow. Now, what I can do to make this symbol tell me a little bit more about itself is I'm adding these. These symbols, by adding the little slash marks like these to a piping diagram, means that that is a flanged T. In other words, that is how it will join its fellow pipe. Okay? The one little slash mark on the others, on this one, means that it is threaded. Another thing this thing can tell me is it tells me what size I'm going from. In this case, I have a size 2 pipe going to a size 4. In other words, I'm reducing from 2 size 4s to a 2. Okay? Does that make sense? I'm combining multiple things to create another set of a symbol. So what we have to look for with this is, what are the drawing symbols? What am I looking for? I'm looking for, if it's my specific trade, I'm going to start looking for what? I'm looking for my symbols, right? If I'm electrical, I'm looking for electrical symbols. If I'm piping, a plumber, HVAC, I'm looking for my symbols because that is the language I know, right? Sort of like if you are, and we'll keep up with German. If you're German, their alphabet's a little bit different than ours, right? They have some different symbols and stuff. Or you're, if you're Spanish and you speak Spanish, there's certain symbols you look for in that. It's all about the language, right? So this is its own language. Electrical is its own language. Hydraulics, pneumatics, its own language. So you look for what is similar. Sort of like, I don't know if you've ever, and how many of you have ever gone traveling? even if it's just like to Mexico, then you know you're looking for what? You mentally start looking for where is English, right? Where is something I'm familiar with that I can read, right? You know what I'm talking about? Most symbols will have something in native language, but they also generally have something in English. Since English is one of the most commonly spoken languages worldwide, um, a lot of countries tend to want to learn English. So you're looking for what is familiar. What symbols are used? Is it my symbols or is it somebody else's symbols? Well, if the symbols can't tell me what I'm looking for, I'll look for the drawing title. Truthfully, I'll look for the drawing title first, then the legend. The symbols used is probably like the last thing you kind of look for. You start looking for the other things first. You look at the title of the drawing. Normally the drawing will tell you what it is. It'll sit there and say, this is the air conditioning schematic electrical side. Or it'll say, you know, this is this house electrical schematic or electrical. If you can't find it on the drawing title, you look to the legend. Does the legend tell you anything? Sometimes there's a legend, sometimes there's not, but the legend and the list of parts kind of tend to go hand in hand sometimes. And something somewhere in that should tell you what you're looking at. Are you using pipe? Are you using electrical wire? Are you using switches? What are you using? Looking for numbers and drawing notes are a big thing. Symbols used. Those three are the last ones you kind of go to. Most of the time, there is something in the drawing title that will tell you what it is. Why? Because it makes it so much easier, and then the engineer doesn't get fussed at. If you don't know the truth. Arranging components. Okay? We're going to look for what? We always look for our source. Our source should always be first. Why should our source be first? Because the source is the most important thing, right? It is the source of all things. Switches are kind of a major thing, especially with anything to do with electricity, because it allows us to turn things on and off. But are switches 100% necessary? Truthfully, no. Switches are not 100% necessary simply because the most basic thing that you can ever do is take a light bulb, a battery, and some wire. No switch required. The switch is one of the most useful things, but it is not required. And then you have always got some sort of straight line somewhere. Okay. You have different kind of views of a fitting, and we'll talk more about these when we get to that particular section of all this. You have the different fitting connections. Again, we'll get deeper into that once we get to that chapter. Let's talk about pipe diameters. Actually, let's talk about nominal measurements. Okay. Might borrow y'all here in just a minute to get some pictures because we're trying to get some new flyers done. Y'all could be the new face of our program. Not the billboard, but we got flyers we're going to be handing out everywhere to try and get more people in the program. So let's talk. Okay, so back to what I was talking about. Okay, sorry guys, I got distracted. So nominal measurements. How many of you have ever actually physically measured a 2x4? Is it exactly 2 inches by 4 inches? No, it tends to be somewhere, I think it's like 1 3/4 of an inch by 3 3/4 of an inch, it's not actually a 2x4. Why? Well, because by the time they finish making the board and shaping it and making it whatever, it no longer is a 2x4, it's less. Okay? The same tends to go for things like pipes. Lots of things in everything you do, if you actually stop and measure it, it's not exactly what it is saying to be. Okay? That's not even just a 2x4, that's like a 4x8. Any wood size is not exactly what it says it is. Does that make sense? It's kind of like, for those of you that have been in EET 100, why do we have a tolerance on resistors? Because they're not always exactly the size they say they are, right? Sometimes they're a little different. So pipe dimensions, we call it something like a 1/2 inch standard pipe. But none of the measurements are a 1/2 inch. It's a nominal number. Now, if I go for an extra thick one, the outside diameter stays the same. The inner diameter is what tends to take on the extra thickness. Okay? And that's true for a lot of this. The outer diameter is not going to change no matter what wall thickness it is. It's the inner diameter that does change. So we'll kind of get into a bit more of that when we get there. The whole thing is it's about tolerances. Similar symbols. So you have a normally open push button, normally closed push buttons. They look very, very similar. You have sequence valves versus pressure reducing. A lot of symbols tend to look the same. It's up to you to be able to do what? It's kind of like the 3 there's. There, and there. Right? Don't know what I'm talking about. You have I might have misspelled that last one. So don't fuss at me about my spelling. But you have the 3 there's. How do I know which one's which? Well, it helps if I have it in context, right? The same thing for any symbol. It might look similar to another symbol, but you have to read it in context. Does it make sense? Normally open versus normally closed valves. Again, reading it in context. We'll get into that when we go into hydraulics pneumatics. So intersecting and crossover lines. There is a difference, and I've said this before, and I'm going to say it again. If you see the dot, that's a connection. No dot, no connection. Okay? Why? Because if you intersect something, you want it to actually intersect. You don't want to put a connection point where it's not supposed to be. Okay? All right. Y'all ready for another break? We'll pause this out for a minute. I'll give you a participation grade. So 3 views and symbols. You've got a line view, you've got an overhead and an underneath view. Now, why would that be important is because, again, you might be having to look down on something like, I don't know, plumbing pipes, or you might be having to look up at something. Because plumbing tends to run in the walls and in the ceiling, especially if you have a second floor or in the floor. So fluid power lines, you have the working, you have the pilot, drain, you have, and of course, direction of flow. Biggest thing here is anytime you see that little black dot, that means it's a what? It's a connection point. To show you, connection, 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 connection. Versus this, which means that it's jumping over it. Okay. And then this is your basic ignition system. You've got your ignition coils here and your ignition switch with your voltage coming in. Which, by the way, what is the voltage in your car? 12 volts from a battery, right? So any questions on chapter 2, guys? Okay.